Here today is Richard Miller on new insights into the polar depth distribution of hydrogen at the lunar poles. I know that you've been coached in how to run the presentation, so
see if I remember.
Take it away, Rich.
All right, thank you very much. It's a pleasure to be here. What I want to tell you about today is a work in progress. I want to give you some ideas of the direction we're going and the work that we're building on. And it really starts, it's a little hard to see. What we've done over the last couple of years is done a comprehensive reanalysis of global data sets, neutron data sets, concentrating on the lunar poles. And the reason for doing this was motivated by the following, that in contrast to some of the other probes of volatiles at the lunar poles and Mercury and elsewhere, neutrons are a low signal to noise investigation. And so using the proper statistical analysis is critically important. When I come from the world of high energy astrophysics, and I've seen lots of 3 sigma results disappear because this robust statistical techniques were not used, and you can fool yourself into seeing something that may not be there. So this really started with developing a statistical framework that incorporates exposures, experimental exposures, and tries to cast the problem into a counting statistics problem. And using that, we've reevaluated the polar hydrogen abundances in a second paper, and also looked at some systematic issues between land and lunar prospector to try and get at some of those questions. And really this culminated this year with the publication of a paper using the statistical framework in which we identified a localized fast neutron deficit that was coincident or consistent with Shackleton crater, indicating the presence of surficial water within that region. And what I want to do now, while we've looked at the spatial distribution of hydrogen abundances at the lunar poles, I want to talk about work that we're doing to go after the third dimension, depth. Oops, already forgot my directions. So what I'm going to do today is concentrate on fast and epithermal neutrons. For those of us in the community, we're usually talk about epithermal neutrons probing down to 1 meter or so in the regolith, and fast neutrons being sensitive to hydrogen deposits in very near the surface. But what I'm going to try to do is bring together those 2 data sets and analyze them jointly to get after more robust estimates. I'm going to only concentrate on the data from the Lunar Prospector mission, in particular the data from the low Lunar Prospector data set where the nominal orbital altitude was about 30 kilometers. So we spatially resolve the exposure, the count rates, and the significances. Because of limited time, I'm not going to go through that analysis. I've talked about that before at previous forums. Except I want to remind you of the following, that the statistical methodology we use, because we're in this low signal to noise regime, is really critical. We want to characterize the significance of these observations when incorporating the observational exposure so that we can have robust estimates. This technique, statistical approach that we've borrowed from astrophysics and applied here serves a number of purposes. Not only can we identify the statistical significance of localized hydrogen enhancements, but in the absence of seeing a signal, we can set confidence level limits on abundances or faster epithermal neutrons, and that's critical to this analysis. So the data space that we're going to use looks like this. Along the horizontal axis is relative epithermal rate relative to a dry regolith at the far end here. Along the vertical axis is relative fast neutron counts. And the contours you see here were derived from Monte Carlo simulations and they represent, the black contours represent burial depth, where we've only considered a hydrogen or water layer with a dry regolith above it at various burial depths. And the red curves, the red contours correspond to fixed hydrogen abundance in this data space as well. So we're going to use this to analyze our data. So what we do is we take this lunar prospector low data set, epithermal and fast neutrons, spatially resolved with a spatial resolution corresponding to the appropriate footprint. And using those pixels, the spatially resolved pixels, we can plot the polar distributions in this data space. So the top plot is the south lunar pole, where the poles are defined north of or south of 80 degrees. In the south plot, you see the red stars there that I've labeled Shackleton. Those are special. Those are where we've found a fast neutron detection, i.e. a 5 sigma significant deficit in fast neutrons indicative of superficial hydrogen deposit. And the blue curves, the blue dots are statistically significant epithermal detections, but because we only detected fast neutrons in that Shackleton region, I've used the statistical methodology to set upper limits on the deficit of fast neutrons, which give me a limit on the hydrogen abundance. So the vertical axis is based on upper limits based using this statistical technique. You also see the north lunar pole here. If we have anything that lies below that 1 centimeter curve, the bottom black curve on each plot, would be technically identified as a surface deposit, but again, this is, except for those Shackleton points, this is using upper limits that are statistically robust. And we also use a forward model to get surface rates here. So what does this all mean? This is a little bit easier to see, maybe. These are plots of depth distributions for both the North and South Pole. Now what I want to be clear here, because we only have positive fast neutron detection in that Shackleton regime, these are based on upper limits. So I'll get back to it, but there is a caveat here that one needs to be aware of. It's a little difficult to see on this plot, but the depth, this is the lower limit, or as shallow as the hydrogen deposit could be, or we would have seen it in fast neutrons as well as epithermal neutrons. So the scale here goes from the surface 0 down to about 30 centimeters. You see generally a circumpolar distribution with some features. For instance, Cabeus sticks out. The missing data in the middle of the South Pole there corresponds to the superficial quote-unquote Shackleton detections of fast neutrons that I identified previously. I just wanted to leave it out here so you see what comes from the upper limits alone. If I ignore those Shackleton, the localized Shackleton feature consistent with Shackleton here, and just look at what the upper limits give me, these are the depth distributions that one obtains. Now, what's important to note here is, before I go on, let me show you the derived hydrogen abundances, again, using this joint fast and epithermal neutrons in that data space that I showed you. These are the distributions of hydrogen abundances. Again, it's a little difficult to see here. You see a general circumpolar distribution with features that do correlate to some topography. We're doing more work to see how this correlates to insulation, etc. But again, you can see Cabeus there, which appears to be an enhancement, and some features in the North Pole as well. But again, these are derived in part from statistically robust limits using our methodology. But they are consistent with the epithermal detections. So you see these features, and it's important to note, are there experimental biases that are driving this? So this is work that we're doing. I don't fully understand the systematics yet or what the level of systematics are, but let me tell you where we're going. The exposure of Lunar Prospector was in a polar orbit, and so there's a great deal more exposure as you get closer to the poles than as you than away from the poles. And if you, because the upper limits on fast neutrons, which are telling you something about whether there's surface deposits or not, the upper limit on the fast neutron deficits that you set are dependent on the exposures. The more exposure you have somewhere and still don't see a fast neutron suppression indicative of surface hydrogen, the more strict or restrictive an abundance and depth determination you can make. This is seen in the lower plot here where I've taken the depth measurements, the depth determinations as a function of exposure, and you can see the large exposure which occurs near the pole gives you the best or most significant restriction on the depth determination. So there is a systematic there. And we can play a couple games, and this is the work that we're starting to do. Here's a schematic of what's going on. The pole has the most exposure, and if we ignore the Shackleton detection for a second, what this is saying is the absence of a fast neutron signature says any hydrogen had to be buried a minimum of 30 centimeters below the surface. But because we have less exposure as you go away from the pole, that depth determination is less restrictive. Okay? And part of that is driven by some of these exposure systematics. But we can play a game here, a Monte Carlo game, where we can pull from the relevant distributions. For example, these are two instances of a Monte Carlo scenario where we picked a fixed hydrogen abundance, pulled from the exposure distribution, and asked what would the derived depth distribution be, which is on the bottom here. Let me summarize since I'm running out of time. This is what the data tells you. Those were the Monte Carlo examples, 2 examples of Monte Carlo. This is what the data tells you. At first glance, this looks like just a random scatter plot. It is not. The red line is there to help guide your eye. It's not used in the analysis, but here you have hydrogen abundance derived from this joint fast epithermal data set versus the burial depth of that hydrogen. And what I can tell you, I don't want to give a firm statistical significance answer. What I can tell you is this is neither random nor is it consistent with a constant hydrogen abundance as a function of depth. There are some gradients here. There is a significant difference between the data below about 15 centimeters and the data above 15 centimeters. There are significant differences. I don't fully understand them or their relevance, but there are gradients here, and they do not come from the simplest models, for instance, constant abundance, or strictly derived from the systematics of the exposure. There's some real structure in here. And perhaps we're reaching the limit of what we can squeeze out of the data, but if you squint a little bit, there might be evidence. What we're trying to get at is there evidence of a thermal profile here, and with a little more work, we might be able to get there. So let me summarize just really quickly. This is a continuation of work we're doing to do a reanalysis on the global neutron data sets, concentrating on the Lunar Prospector, to take that from a qualitative analysis to a quantitative analysis, and by doing that, we're seeing features that are statistically robust and are giving us some additional insight about polar hydrogen distributions. We may have evidence, again, I want to be a little careful here, for non-uniformity of abundances as a function of depth. This is intriguing. It probably won't be conclusive. I want to raise some caution. This is derived using upper limits. Again, this is the best one can do given the data. But what I hope this does is motivate some future investigations that if we really want to understand the polar hydrogen distributions, we'll need some additional exposure. There's some benefits to, in astrophysics, what we call a multi-messenger approach, i.e. not just doing epithermal neutrons or fast neutrons, but a joint analysis to get at not just spatial distributions, but depth distributions that can tell us something about the sources as well as their potential migration or evolution with time. So, thank you.
Okay, thank you, Rich. I'm afraid you have perfectly packed your time,
That's
so
fine.
there was